Alright, looking at ways we can take a traditional y equals f of x type function and turn it into a power series. And there are multiple ways you can do this. And every function can be turned into a power series through one method or another. But the easiest method is what we're going to look at here, and that is to take your function and see if you can manipulate it in some way so that it resembles the formula for the sum of an infinite geometric series, which that formula would be the first term over 1 minus the ratio. And I do need to throw in here that this is only true if the absolute value of your ratio is less than 1. So there is that one little caveat that this is only true for a ratio that is between -1 and 1. And so let's look at a few examples of how we're going to do this. And the first one is about as straightforward as it comes. That box needs to go away. There it is. So I'm looking at this and I see 1 over 1 minus x, and that definitely looks like a sub 1 over 1 minus r. And in this formula, my first term is 1. The ratio is replaced by an x. So then I could say that this function can be represented by the series from 0 to infinity of my first term times my ratio to the nth power, and that is a representation of that function. But you have to remember that the series only converges if the ratio, well, can't spell for, only if the ratio, which in this case is x, if the absolute value of that is less than 1. And so while yes, this power series does represent this function, it can only reliably be used for values of x between -1 and 1. If you want to approximate f of x with the series, and you want to plug in 2, that would be a really bad idea because you're outside of this is your interval of convergence. So let's look at another one. This one's a little bit more complex. I do still see something over, and I see a sum down here, so it does resemble first term over 1 minus the ratio, but I really want it to be a minus sign down here. And so I'm going to fix that by changing it to 1 over 1 minus a negative x squared. If I do that now, I do have 1 minus in the denominator, and that's the key part. My first term is 1. The ratio is negative x squared. So that I can take all of that information and rewrite that into a series. That would be first term times the ratio negative x squared to the n power. And there you go. And again, the interval of convergence, this is only viable, this power series is only a good representation for this function if the absolute value of your ratio is less than 1. That turns into x squared is less than 1, and if you solve that, that's going to be, again, for all x's between -1 and 1. So remember that these are power series representations of the functions, but only on the interval of convergence, and that's how we will do number 2. Okay, so here another one. I see 1 over 4 minus x. I see the minus sign, which I like. However, this one, it's not 1 minus the ratio, it's 4, and that 4 has to be a 1. So I'm going to fix that by dividing it by 4, because 4 divided by 4 is 1, but if I divide that by 4, I've got to divide every other piece of this fraction by 4. So now my function is rewritten as 1/4 over 1 minus x over 4, and now I'm in my geometric sum format. First term is 1/4, ratio, x over 4, and so I can take all of that and put that into a series 0 to infinity of my first term times the ratio to the nth power. And it may not be a bad idea, I haven't stressed this on the first few, but it may not be a bad idea after you have written what you think the series is, to check and make sure that you do have the correct ratio and the first term. Ratio is pretty easy to see. The ratio is the part that is being raised to the n power, and then just verify, plug in 0 for your n, or wherever you're starting, and if I plug in 0 for n, I have 1/4 times stuff to the 0th power, which would give me 1/4 for my first term. So always verify when you plug things in, verify when you write your series that it actually does yield the correct first term and ratio. Don't just always trust your formula right off the bat. So back to this one. So we have this series. The ratio is x minus 4, x over 4. If I need the absolute value of that to be less than 1, and if you solve that, this one has a larger interval of convergence. We can actually go from -4 to 4. There's your interval of convergence. And sometimes it's advantageous to rewrite and clean up your series. And so in this case, that's x to the n over 4 to the n. That's 1/4 x to the n over 4 to the n. And then I could even go one step further and write that as x to the n over, and I have 4 times 4 to the n would be 4 to the n plus 1. And depending on the question and what all is asked, or what you may have to do to the series, it may be beneficial to have it written in this format versus your traditional geometric series format. But all of these are acceptable series representations for this function. And then this is the last one I wanted to look at. Whoa. This is the last one I wanted to look at. I don't like having the x first. I would rather have the 2 first. So how about a very tiny, insultingly easy first step? Let's make that 2 plus. And here I kind of have the same situation I had on the last problem. I don't like having the 2. I would rather it be 1, because the sum of a geometric series is 1 minus the ratio. So we'll start by dividing everything by 2. And that's going to give me x cubed over 2 over 1 plus x over 2. And then I really want that to be minus. It's supposed to be 1 minus the ratio. So I'm going to change that denominator to 1 minus a negative x over 2. And now I'm looking at that, and I can see that my first term is x cubed over 2. My ratio is going to be negative x over 2. And I can put that into a geometric formula, geometric sum series. I'll get it right eventually. X cubed over 2 times negative x over 2 to the nth power. And then for my interval of convergence, I need the absolute value of that ratio to be less than 1. That's going to be when absolute x over 2 is less than 1. Absolute x is less than 2. So we need x's to be between -2 and 2. So there's your interval of convergence. And if you wanted to rewrite this and separate all the terms out, that's x cubed times -1 to the n times x to the n over 2 times 2 to the n, which then can be rewritten as -1 to the n x to the 3 plus n over 2 to the n plus 1. And this is still starting at 0, going to infinity, and all of those are good power series representations of this function, again only for the specified interval of convergence. And that is your first way of turning a function into a power series, and we will learn a couple of other methods later on in your life.